So, hello everyone, it's great to be here. I'm going to be saying a few things about neural differential equations, as you may have guessed. So, today's program, I'm going to be going over kind of as, like, in some sense, this is an overview of the whole field. And so I'm going to be giving you an introduction, some words on neural ODEs, neural controlled differential equations, neural SDEs, and then also some discussion on the numerics and software. But in practice, you can see that I've bolded those last few points, and that's because that's really where I'm going to be biasing the discussion and spending most of the time talking about. I'm doing this on the assumption that probably a decent chunk of the audience has seen neural ODEs before, has some sense of how a lot of these things fit together, and neural CDEs now, these are now a couple of years old, so maybe you've seen this before too. So I'm gonna bias towards the end and hopefully on something that's new and interesting. If you do want this but more, this but bigger, as David said, my thesis, this now exists and more of it exists on archive. So if you want basically a textbook, it's explicitly just a textbook of NDEs. Go have a look at that. And it will of course be discussing all kinds of things that I won't get into today, including a bunch of unpublished material. So this is things like reversible differential equation solvers, Brownian reconstruction, generalized backpropagation, and symbolic regression. So if any of those things sound interesting, go check those out, because I won't be covering them today. With that quick advert out the way, let's get on with the show. So I have one slide's worth of neural ODEs, just to lay the scene. So what is a neural differential equation? It's a differential equation with a neural network vector field. So the canonical example, of course, is the neural ODE. You can see I've just written down a generic looking ODE, and every time you see a subscript theta throughout any of these slides, subscript theta, just think that's a network, that's a neural network. So in this case, that's all it is. And today I'll often be thinking of it as a feed-forward neural network. In practice, you have a million asterisks against this. In practice, maybe you want to do something else. In practice, there's all kinds of things you need to worry about. But we're not really going to do in practice today. So this is just a simple thing to be thinking of. In terms of references for this, by the way, the paper everyone knows about, of course, is Wikki's paper from 2018. This is best paper in Europe's 2018. But actually, of course, as with anything in deep learning, it was secretly done by some guy in the 90s. And this is equally true here as it is anything else. And indeed, there are others more than this way. You can easily dig up at least half a dozen different papers doing different flavors of this kind of stuff. So why is this a reasonable thing to be looking at? This sort of weird nested neural network inside a differential equation. And the justification I like to give for those coming from applied mathematics backgrounds is that this is what you've secretly been doing all along anyway. If you look at, in this case, it's the SIR model. This is just a model from mathematical epidemiology. It's some theoretical model. And you can see I've got some parameters. You can see I'm using a convergent hill. The parameters are in blue. I have some evolving state, SINR, here in red. And you can see that I've written down this ODE, and that actually there's very little difference between this thing and the thing I wrote down higher up the slide. Both of these are parameterized differential equations. Both of these use some kind of theoretical model for that right-hand side. And the only difference is that in the case of the SIR model, it's something designed to fit a particular phenomena, in this case, the evolution of a disease, and it's known to be very good at fitting that one thing. Whereas in the case of, say, the neural ODE, it's a neural network which has approximation capabilities and is known to be very good at approximating lots of things. So that's the justification there. And then again, probably many of you have already seen this, but if you're coming from deep learning, then you take a neural ODE, you apply the explicit Euler method, and you get out a residual network. So this sort of the story here, conversely, is that if you do deep learning and care about deep learning, then actually neural differential equations are somehow secretly already there. This point about the connection between neural differential equations and deep learning, there's actually quite a lot of these. The famous one is undoubtedly residual networks, the one I've already given. But if you go burrowing through the literature, you'll start noticing that things like GRUs and LSTMs, the things that these have relative to generic recurrent neural networks is a differential equation-like structure. It very explicitly looks like the thing that makes these work, the thing that makes them better than off-the-shelf Rnns, is a differential equation-like structure. If you look at lots of generative models, these are basically SDEs. If you look at things like coupling layers and things like invertible neural networks or normalizing flows, these are a generalized version of reversible differential equation solvers. There's been some interesting bits in the theory of deep learning recently, which when you sort of translate them over this continuous time thing, mean that you get exponential decay terms appearing in your differential equation. And it somehow seems that you have to have these exponential decay terms in order to get good behavior in various limits. And ... you get the idea. So there's lots of kind of like interesting things that I think motivate this as a worthy topic to kind of draw connections with. And then in terms of applications, well, where do we actually use neural differential equations directly? There's, I think, well, first of all the things we're already using them for. Probably that isn't news. We're already using diffeqs in these cases. Let's keep using them. And indeed, let's augment them with neural networks. If you look at things like time series, then this ubiquitously has irregular data. And how do you handle irregular data? Well, one really nice thing to do is to push that into continuous time. And I'll touch on that later too. Generative modeling, I'm going to be talking about neural SDEs a little bit later. It turns out that lots and lots of generative models are well inspired by SDEs. And finally, inspiration. Lots and lots of discrete deep learning is still very, very useful. It's not going anywhere because it's still very, very helpful. And we shouldn't feel bad about using a differential equation and then explicitly discretizing that and using that as inspiration. So with that is a couple slides of introduction, and maybe some of that wasn't news for folks. Let's crack on to neural controlled differential equations. This may be new to some folks here. So first of all, let's write down a neural ODE. You can see this is just a standard looking neural ODE. I've just written it in integral form. It happens to be autonomous. These aren't terribly important choices. And this takes us as a single input. You've got this initial condition. But what do we do if we observe some ordered data and we want to fit in this ordered sequence of data into this integral? How do we do that? The intuition is that we're going to want to do something that looks a little bit like this, some way of inserting this data as our differential equation, as our integral proceeds. And in doing so, we'll build a model that depends upon not just a single input, but upon a sequence of inputs. And so this is where, first of all, I'm now going to scrub that word neural in front, because as you probably guessed, what I'm going to do is I'm going to tell you what a controlled differential equation is, and then we're just going to jam a neural network in there in the appropriate spot. So the idea of a controlled differential equation is that we want the local dynamics of the system to depend upon some time-varying input. And moreover, I'm going to do so in this particular form, where you can see I've written down that integral. And the difference now is that this input here comes in as a Riemann-Stieltjes integral. So f dx is a matrix vector product. F is a matrix, x is a vector. And don't worry if you have either not seen or have forgotten what a Riemann-Stieltjes integral is. I appreciate in particular not everyone comes from a mathematics background, pure mathematics background. Then as long as x is suitably smooth, then you can actually reinterpret it like this. And this ends up being a really natural way to incorporate incoming data into your system. It's essentially the x determines the local notion of physics for your differential equation. And fundamentally, this what I've written down here, this is a controlled differential equation, and it's an operator on path space. It's a thing that takes in an input path x and then produces an output path y. And moreover, it does so whilst preserving some notion of causality. If you're a mathematician, you might say measurability with respect to a filtration. It encodes this fact that the future can't affect the past. And it's a very generic way of encoding such operators. So I'm moving relatively fast, by the way, on the assumption that this is maybe familiar to some people. Please tell me to jump, David in particular, please jump in and tell me to slow down or speed up as you see appropriate. So yeah, okay, moving on. Let's reinstate that word neural. Let's take this thing I've just told you about and use it to learn something. So we're going to assume I observe some continuous sequence of observed data. And this may be an interpolation of a time series. Time series are discrete. Join up the dots, get something continuous. There are other things we can do here. There's, again, asterisks and things. But let's just stick with this for now. And we're going to try and learn some neural networks such that this initial condition is a function of where we started. That's the same as what we wrote down a couple of slides ago for the neural ODE case. And the difference, as you can probably guess, is that we're going to have this controlled differential equation that now has input at the rest of this x, the rest of this continuous time path x. And so the output is then going to be a function of either y at capital T, y at the end, or y is the evolving state t. And I realize I've been talking quite a lot, and that's quite a lot of words. So let's just give some brief point of intuition. Why am I constructing all of this mathematical tower? And the basic idea is that what I've written down is a continuous time Rn. This is what I promised you in the introduction. We were going to look at this link between, say, an Rn and a continuous time version of it. And that's exactly what I've done here. In the Rn, we had this discrete input x, and this provokes changes in this hidden state y. And then once again, you see exactly the same thing here for controlled differential equation, that you have your data x, and this provokes changes continuously in this y. And I think the key thing to really sort of take away from this is that Y is hidden state. In the case of an Rn, Y is hidden state, and I have some map from hidden state to output. In the case of the CDE, Y is hidden state, and then I have this L that is a map from hidden state to output. And so, well, A, that makes sense in terms of an analogy. But B, what I'm saying here is I'm writing down a differential equation in a latent space. I'm not writing down a differential equation in data space. This is just a common point of confusion that I want to head off. I'm not trying to use my differential equation to predict something directly. I'm using it to evolve in a latent space. And in doing so, as a mathematician, I would say that I'm potentially modeling something non-Markov. That by having this latent extra data available to me, then my output here it may evolve in non-Markov ways with respect to itself. And if you're not a mathematician, don't worry. Just think of it as hidden state, and that's probably familiar. So what's like the intuition here is that I've observed some, looked out into the world, and I've seen some data X. At times Ti, I make observations Xi, and then I join up the dots, as I sort of said at the start of this slide, into some continuous path X, capital X, and then I use that to drive my Y in continuous time. And in some sense, this is going to be the single most important slide in the whole talk, because we're going to keep coming back to controlled differential equations again and again as we go through this talk. They're going to appear in the SDEs, they're going to appear in the software, in fact, as well. They turn out to be a unifying theme. I think it's a very important abstraction. So this is kind of why I'm belaboring this point a little bit. I want to make sure that people are on board with controlled differential equations, that this feels like a thing that you're relatively comfortable using, at least in terms of the intuition. And if it isn't, in fact, I'm seeing chats and Q&A notifications. Maybe now would be a good time to look at that, just in case that isn't the case. So, is the observed time series used to train the network for a complete observation of the state space? So, depends what we mean by state space. In this case, I usually think of the state space as meaning Y, in which case we never observe the state space. The state space is latent. I never observe data for this. My model would never output this directly. So I'm not sure if I've answered your question, if I've interpreted your question correctly. Feel free to clarify if not.
I guess I would say, I think the answer is clearly no. And that this is a huge strength of this whole approach, is that it can take sort of the raw, irregularly sampled data, which I think there has been, previous work that said, oh, let's assume we see the entire trajectory, or at least at some very fine discretization, which is certainly like easy mode, right? Because then you can just learn the instantaneous dynamics. This is the fancy probabilistic mode, or at least that's what you're building towards, I guess.
Cool. I think our anonymous attendee is happy with the explanation. Thanks for jumping in, David.
Okay, but there is another anonymous attendee who asks about, wants to compare this to Rnns.
Okay, so can I expand on this, how this is an Rn? Basically, it's a continuous time Rn. In the case of an Rn, you can see I've written this down here at the bottom. I have some discrete Y, I have some discrete X. Every time I observe an X, I update my Y. Every time the next time I observe my X, I update my Y again. Keep doing that, and just keep doing that. Oh, it's exactly the same.
Sorry, I guess one
thing. Please, David, jump in.
I guess I've found this point confusing, is that there's sort of like at least three flavors of Rnns. One where the hidden state updates based on the data at every step, and another one where the Rn just generates predictions for the data, like the decoder of a sequence model. And then there's the sort of hybrid one for like text generation, where you both predict and condition on the next data point at every time. As far as I understand, this is really corresponding to the encoder of a sequence-to-sequence model, where we're just having the hidden state depend on the data at every time and update a little bit, but we haven't really talked about predictions or decoding or anything yet.
Yeah, you're absolutely right. This is, I think, one of the slight disadvantages of the machine learning literature, which has chosen to use Rn to refer to several subtly different concepts. And actually, when I get onto SDEs later, I'm going to be telling you that SDEs are also continuous time Rnns. And it's because the mathematics literature has actually made this distinction for some slightly different concepts, and the machine learning literature hasn't. So in this case, when I say Rn on this slide, I mean exactly this. It's just this thing that provokes a change in hidden state, and that's it. And then up here, you can see that it's exactly the same thing, as X is there as an input into my integral. And remember, I told you if you don't know what a dx, if you're not familiar with the Riemann-Stieltjes integral, just mentally substitute that thing I have on the previous slide, with dx, ds. And you can see that because x is on the right-hand side, it's affecting the evolution of that y. And as a result, it's provoking changes in y just continuously rather than in discrete time. And there's obviously all kinds of little twitty little things I could go into there. But basically, that's the intuition. It's a continuous time Rn. Okay, I think I'm going to move on. So, in fact, I should have just seen someone else say something in the chat. I'm trying to make sure I'm clear on these three objects we're learning. Is the output of L theta in the same space as X? Not quite. Okay, so this is kind of the next thing that I'm about to get onto, which is if you think about having something like an Rn, then an Rn is, for the purpose of this discussion, you're trying to learn a function of a time series. You have some time series, you feed it into your Rn evolves along, spits out some hidden vector. And then I have a function from that hidden vector to my output. And my output might be something else entirely, right? It might be a binary classification. Does this time series correspond to a patient at risk of sepsis or not? Yes, no. And you're doing binary time series classification. And it's exactly the same here. That here I have some capital X, this is my input data, which may be, by the way, just in this interpolation of my little xn of this discrete thing, if I wish. I have this input data, this provokes this change in the hidden state y. I then have some function of my hidden state y and get some output, this L of y. And now this thing may be, for example, a result of that binary classification. That might be the thing that says, this patient is at risk of sepsis, yes, no. So the whole overall, a CDE is about learning a function of a path. And so in fact, maybe it's helpful if I go back a slide and demonstrate. Here, a CDE is an operator from X to Y. So the input is X. The output of this thing here is just this evolving hidden state Y. And then the output of my model is some function of that hidden state. I realize I may have gone through this slightly too fast. As I said, this is a couple of years old now, so I was sort of assuming that this may have been something some of the audience have seen, but I think maybe that might not be the case. Do people feel okay with this? Should I keep going? As I said, this is important. I want to make sure this is clear. David, I'll leave it up to you.
Well, sorry, I actually just got distracted for a second. Did you see Rachel Kirchin's question here in the chat?
Yeah, that's what I was just addressing.
Okay, great. Yeah, that's what I thought. I just wasn't totally sure. Okay, great. I mean, I guess to me, I didn't understand neural CDEs until I understood that you were just using this as a way to condition on discrete data in a continuous way. So I would probably move on to that and then ask again. Okay.
So moving on, I think was the answer there. So going on.
Oh, so we have a question in the Q&A though.
Is it always a multiplicative factor, or can it also be a function of dxs? So for the purpose of this talk, it's always this multiplicative thing on the right-hand side. In practice, you can start looking at other things. In practice, you can start wondering about other kinds of dependency. And there are sort of upsides and downsides to doing that or not doing that. But for simplicity, I'm just going to talk about this particular form today. And if you want like a quick rationale for that before we get onto it later, I want you to think of something like a stochastic differential equation, where you're used to writing down like dws or dwt, right, on the right-hand side. And in that case, you can envisage other ways of making a differential equation be random. It doesn't have to be a Brownian motion driver like that. You can do all kinds of things. And in this case, that happens to work very well for SDEs. And so maybe in some sense, for simplicity, I'm going to keep doing the same thing here, just for other drivers now that are non-Brownian. How would the variations in RNN architectures like GRL STM look under this formalism? Right. So I don't have these written down explicitly, but I do have it written down elsewhere, certainly in the thesis, which is basically you can take something like a glue, you can continuize it, turn it into a differential equation, and you can explicitly write it down in this form. In terms of what it looks like, it's a differential equation. I don't think it'd be that helpful to break it apart whilst gesticulating over the internet. I can try and use this as a limit test. X is observed data, Y is some latent space, which we get from X using zeta. F is a derivative of the latent variable Y, which will evolve in time, and then map to our desired output, which is thus named thus far correct. Yep, using L theta, if this is correct, at least this particular attendee. Oh, sorry, I've scrolled slightly too far. is now clear on the notation. Okay, yeah, you're completely correct. So I think with that litmus test passed, I'll move on to the next slide. So examples of where you might do this kind of stuff, and maybe this will speak to some of this as well. Basically, it's kind of all the things you're used to thinking of when you write down a time series. So I have a time series ti xi, so at time t I've observed xi, join up the dots, say, feed all of this in, and now maybe that time series is the evolution of a pen as it moves over paper, and I write the letter A or the letter B or something, and now I want to do some kind of classification. Did they write the letter A? Did they write the letter B? Da, 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 da. Patient hospital records. This is an example I quite like, because you can imagine that you have some collection of observations that says a patient had a heart rate this at this time, lab result something else at some other time, and so on. And you end up with this irregular time series that you want to work with. And now you want to continuously perhaps predict, is this patient at risk of sepsis? Yes, no. And you keep updating that prediction. Do I think this patient is at risk of sepsis? Yes, no. Keep going. And so this is another example of where you have this function from a time series to something you're trying to predict, something you're trying to say about that time series. And of course, at this point, you can start sort of open Pandora's box and think of any old time series. You could do spoken audio classification. You could look at things like weather data. You could look at things like physics, and start trying to model any kind of function of these time series. Yeah. So I've been saying controlled differential equation quite a lot. Many of you are probably thinking control theory. What is the link or comparison between CDEs and control theory? So speaking very, very broadly, in control theory, the system is fixed. Maybe it's specified implicitly by a data and you need to do some kind of system identification, but your system is fixed. And now your job is to find an optimal control that produces your desired response. In the case of CDEs, it's kind of flipped around. Your input is fixed, your input is the data, and now your job is to find an optimal system, an optimal F, that produces a desired response Y. So in some sense, the difference is purely philosophical, right? It's just kind of where you're putting the emphasis. This isn't really a distinction I care to enforce. I think both fields probably have a lot to learn from each other, and then that just hasn't happened yet. And I think, to be honest, the division is mostly just historical. So when I say CDEs, I don't mean control theory, but they're links. Now, there are lots of things I haven't told you about. I haven't told you about good choices of F. I said at the start, let's think of it as a feed-forward network, but in practice, maybe you want to do something else. This got touched on earlier. Why this particular form and not some other form? The very, very short answer is that this connects up with the discipline in mathematics known as rough path theory, which is amazing, and I'm not going to get into it today. But if you do start applying rough path theory, you can start doing cool things. You can start applying CDs I describe these as very long time series. I was giving this talk once where someone scoffed and said, it was a short time series. We deal with million lengths time series. And I was forced to agree, I suppose, that perhaps very long is subjective. And in particular, because you're linking up with these strong mathematical disciplines, you can start giving theoretical guarantees. And so, for example, you could say that a controlled differential equation is a universal approximator in a certain sense. It can really approximate lots and lots of things. And this is something where I think frequently people just kind of scoff and say, universal approximation is not that big a deal in practice. Right? You just want something that works. This one actually will be important, and I will come back to that later. You'll see why. This interpolation thing, I keep kind of skirting over the interpolation. There's actually a whole interesting little line of work you can go down here about saying, okay, well, what choice of interpolation scheme should I use? Does it make sense to do an interpolation? And if you're curious, yes, we have a whole paper dissecting this. And then you can also draw more comparisons to Rnns. So there's a few things I haven't told you about, but hopefully I've told you enough that you're convinced that this is an interesting thing to be thinking about. And in particular, I'm now going to be using these as a tool to study neural stochastic differential equations. These are going to be one of the building blocks for working with stochastic differential equations. I think now might be a good time to just quickly pause and ask if anyone has any other questions. In particular, if you're not clear on CDEs, I will be using CDEs a lot. So if anyone is feeling less than clear, I'm very happy to go back over it. Okay, I'm seeing silence. I think people are happy. That's good. So, okay. SDEs, how are we going to start doing this? I appreciate, by the way, not everyone has a background in SDEs. I'm going to try and tell you something that is intelligible, even if you're not that familiar with SDEs. So let's consider this thing here. This is just a generic looking stochastic differential equation. I've just written down something general. And when I say general, I also include the fact that x and w are vector valued, and therefore my drift is vector valued, and in fact my diffusion is now matrix valued. So over here on the right hand side, you see this matrix vector product between the matrix diffusion and the vector control matrix vector noise W. So that's my SDE. And the strong solution for an SDE, what does it mean to solve an SDE? Well, actually, this is something which is probably relatively familiar to people who have thought about like generative models or something in deep learning. It's just a map from noise to output. I have some noise, I have some input noise, things like my Brownian motion and whatever initial distribution I have. And I pass it through a bunch of mathematical machinery known as stochastic integration. And then what do I get out? Well, I get out some distribution over paths. So that's what it means to solve an SDE. And we can sample from this. That's what SDE solvers do. But it's kind of tricky to write down probability densities. There's some asterisks against this. You kind of can, kind of can't. But for the purpose of this discussion today, we can't write down a probability density. And the main mathematical hurdle is that these paths are infinite dimensional because they're paths, right? They're not individual points. And that makes writing down things like probability densities kind of like a tricky thing to do. So that's why I emphasize over path space. And then we're actually looking at this full evolution of X. I'm not just trying to fit the terminal density xt. There are interesting things you can do with that. That's not what we're doing. We're looking at this whole X. And how do you train these things? If you open up like a finance textbook, how do they train these things to like match like market data or something? Well, or at least one way of doing it, is to match statistics. Is to say, I take my model and I evaluate it on some fixed functions f that I know I care about. And I say that the expectation of f on my model should look at the expectation of f on my data. And as long as these things are matched for all f that I care about, then great. I've successfully obtained a model that models the things I care about. It models these f that I care about. So this is what it means to have an SDE. And in particular, I'm not doing any neural network stuff. Yeah, I'm not doing any deep learning stuff.
So can I stop and nitpick your notation or the types here? So you're saying x here is vector valued. Maybe I missed this, but I mean it's actually like vector, like it's function valued. If I'm
right, so I see what you're saying. Okay, so what I'm trying to, I haven't actually written it down. Maybe I should have done. What I'm trying to say is x is a path from say 0t, some interval 0t, and when at every point, x at t is a vector.
Yeah, right. So, but the x without a subscript is actually an entire function, I guess.
Yes, you're correct.
Okay.
Yes, no, I've not written that down super clearly. I think actually you're quite right.
And then I guess there's one other thing which I think everyone does. You said we sample from an SDE. I mean, there is like this equation at the top, which is an SDE, and then you're sampling from the distribution over functions or distribution over paths implied by that SDE.
I mean, if you wish to make that distinction about the SDE and the distribution of paths implied by that SDE, then yes. Personally, I'm not making that distinction when I talk. And to me, an SDE is a distribution over paths.
Sure. Yeah. I mean, I agree that there's a one-to-one correspondence, and then just like on the first day, I guess I think it's worth distinguishing those, just because I think sometimes people are confused when you say I'm going to run my SDE solver, and then it's like, wait, what does it mean to solve this? And I mean, you say there, but anyway.
Yeah. No. That's a reason. And by the way, please keep jumping in like this. This is helpful. I'm really trying to gauge how much is what's clear and what isn't. I
mean, I only started learning about SDEs like 2.5 years ago, and so I still remember all the confusions. So,
yeah. Okay, so I've told you what an SDE is. Now, this may be more familiar to some folks. I'm going to tell you what a Gan is, and if this seems a bit, if you want to know why I'm doing this, you'll see where I'm going in a sec. So, if I have some noise thing. Some random variable that is representing noise, and some other random variable representing the target that I'm trying to model. Then a generative model is a map from one space to the other, such that the distribution obtained by evaluating my network on my noise is approximately equal to the distribution I get by looking at this target random variable B. And to give an example, A might be some sort of multivariate normal, and maybe B is a distribution over pictures of cats. And so this is the general formulation of any kind of generative model that you see in deep learning, right? I ask my computer for a normal random variable, I push it through a bunch of neural network stuff, and I obtain hopefully a picture of a cat. And in distribution, I want my model to look like the distribution of all cats that I've seen during training. So we can obtain samples from this in the way I've just told you. We just sample a normal random variable and push it through all of this neural network. But in general with GANs, you don't have a density function, so you can't train by maximum likelihood. And so instead, what do we do? Again, I'm just sort of telling you standard off-the-shelf GAN theory here. Instead, what we do is we train theta to minimize this distance between my model and my data. And in particular, we define it like this, where f is what we call a discriminator. And so for some of you, probably this is already familiar, where you can see what I've down here on the left-hand side is simply random variable of A, evaluate that on G, so now I get a sample from my model. Over here on the right, I have B, that's a sample from my data. And then I evaluate my discriminator on both and just take an average. And I just ask that my discriminator has to be able to say, yes, no, is this real or fake? And if it can't tell the difference between them, then yeah, I've done a good job. My model's done a good job. And this is perhaps where you start to realize why I've told you these two slides. What we're doing here with the discriminator is matching statistics. I've said that for all discriminators F, all statistics F, this is what this loss function explicitly minimizes, explicitly obtains, is that this statistic, this discriminator, applied to my model should look like the same statistic, the discriminator, applied to my data. And so what you see here actually is that the way people have been training SDEs for decades and the way people have been training GANs for years is actually kind of the same thing. And so having made this observation, you can probably see kind of more or less where we're going to go with this. We're going to try and push this idea a little bit further, and we're going to try and train an SDE as a GAN. So let's do that. Let's write that out. We want to model some B, some random variable on path space. And so, for example, I've looked out into the world, right? I've looked out into the world and I've obtained a time series. And I've looked out into the world and I've got another time series. And I've looked out into the world and I've got another time series. I do it lots and lots of times and I get some distribution over time series. And so maybe, for example, that's the finance is always the go-to example when people talk about SDEs. It's the same here. Maybe I look at the world and I see that the stock market has done this today, and look at it the next day and it's done something else today. Right? Do that a few times and I get a data set over time series. And now I want to model the stock market. That's a bold ambition. But hypothetically, that's what I'm doing here. And now I'm going to set up my GAN. So how am I going to set up my GAN? I'm going to do so by taking some Brownian motion. I'm going to take some initial noise. So these are the things that I told you I needed for an SDE. I'm going to introduce a bunch of neural networks. And then I'm going to write down basically the same SDE I wrote down earlier. Right? You can see it looks very, very similar. So you can say, first of all, I've explicitly told you what the initial distribution is. The initial distribution is some learned function of noise. And so in principle, this could be anything. So I've written down something that could be a very flexible initial distribution. And now I've just gone and written down a general looking SDE with neural network vector fields. And so now I've gone and written down any SDE, quote unquote, any SDE. And then in common with all that discussion we had earlier, my SDE, my differential equation, is actually going to evolve in a latent space. And if I want to actually get an output from it, then I'm going to take some map from my latent space into my target space. And indeed, this is what I formalize quote unquote, by saying that Y should somehow look like B. So I've written down a general looking neural SDE. And what is an SDE? An SDE is a distribution over path space. That's what I told you a couple of slides ago. And I've looked out into the world and I've observed some distribution over time series and just papering over the distinction between a time series and a path. Then you can see that now an SDE can now be a model for what I observe in real life. I sample from my SDE, I get a path. I look out into the world, I get a time series. I want these two things to look the same in distribution. So why have I written down the SDE like this? Well, it has this certain minimal amount of structure. We have hidden state. X is hidden state. And basically this is speaking to that discussion we had several slides ago when I was telling you about controlled differential equations, which is that you need hidden state in general. If I was to write down dy of t equals some stuff, if I was to directly do the evolution in data space, then maybe that's good for Markov processes. But in general life, the thing I observe will not be Markov. In general, I haven't observed my data completely. In general, I've only got a partial observation. And so the way we handle that is by just working in a latent space. And for those of you coming from more of a machine learning, more of a deep learning background, then hopefully this feels entirely familiar, because this is what you always do all the time anyway, right? You have something like an Rnn, you have some hidden state. You evolve some hidden state, right? And so what I'm doing here is the normal thing to be doing.
So I do want to nitpick right here. So you have this y equals L of xt. And I guess, so like here, L is kind of like the likelihood or the emission function or the observation function. And I guess I would not normally write that as a deterministic function, which it looks like you have here.
Right. So if you want to incorporate some randomness, this is, yeah, you can if you wish. So maybe you're thinking of like measurement noise or something. Maybe you have some kind of white noise on top of all of this, representing the independent measurement noise in a sensor.
Oh, I'm thinking here maybe like YT is like text, like maybe it's like a doctor's note or something. So I might be taking some continuous latent state of the patient or the doctor's mind or something, and then turning that into a discrete thing. And so I will have to, sample from some discrete latent variables or some discrete, observation variables. So then it doesn't even really fit in to talk about like adding some white noise or something. We're just sampling locally from this little noise distribution.
So the very, very short version is, yes, you can totally extend this in the way that you're describing. If I wanted to, I could absolutely start putting extra random variables here, some extra stochasticity into my L. I choose not to, mostly for simplicity. You can write down theoretical boring justifications that I won't get into today. But yeah, if you wanted to, you can start extending this. And this is one of the nice things, by the way, about the fact that we're building on top of a GAN and not anything else. Because with GANs, you can just keep inserting stochasticity any way you like. And then at the end of the day, you just feed the whole thing into your discriminator. You don't even care how you generated it. You just keep putting in sources of noise throughout your model. Sure. And the same is not true of something like a VAE.
Sure. Well, so first of all, the only reason I mentioned that is because you said this is maybe the standard way we think about it. And I guess I would say, no, the standard way, yes, I would just write down like a generic likelihood. And two, I guess I would say also in the VAE framework, you can have arbitrary likelihoods and it doesn't hurt anything.
So it gets more complicated in the VAE framework because you start needing to like build an encoder into every single source of noise.
I would say you just have to build one encoder that takes your raw data and goes all the way to the latents. And so all the intermediate steps can be skipped by your encoder.
I think there are points I'd debate, but I feel like we probably shouldn't spend too long doing
so. Yeah. No, that would be yeah.
Let's stick with this formulation for now. And I think we both agree that we can certainly do more complicated things. In fact, I also see someone's got a Q&A question, so let's address that now. So would discrete or noisy L theta actually be defined when it's on continuous xt? If you're sampling at continuous time, what does it mean if the measurement noise is different when infinitesimally close? That would mean YT might have infinite local variance. I think that only makes sense if y of t is only defined at discrete time points. Right, so this does make sense in this kind of stochasticity. The point is simply that y wouldn't be continuous. Right, if you think of something like a white noise process where it's just like an independent Gaussian at every single time, you have no notion of continuity. You could like imagine doing something similar here. You don't have to get a continuous output for y. Let me know if that does or doesn't make sense. How does this moment matching approach connect with the adversarial component that is the central component of GANs? So this is kind of going to be my next slide where I match these two things up against each other. Where basically, okay, so first of all, I wouldn't describe this as moment matching. In some sense, it's kind of a meaningless distinction, but for the purposes of where I'm going to be going with this, I'm very much going to be thinking this as a GAN all the way for both SDEs and for this kind of this GAN stuff I've been telling you about earlier. Maybe the next slide will answer your question. Let's see. So on that note, how do we train these things? The output of my model, the output of my SDE, is a continuous time path y. And so, because I want to train these things as a GAN, because I'm inspired by that stuff I had a couple of slides ago, I want to train these things as a GAN. And so I need to introduce a discriminator that accepts continuous time paths as inputs. And do you remember when I told you about that most important slide early on in the presentation? Well, it's coming back to haunt you now. This is why I told you it was the most important slide. There is a very convenient choice for a discriminator that accepts continuous time paths y. And that choice is a controlled differential equation. And so you can see why I introduced them earlier. And so when I introduced them earlier, controlled differential equations were going to be some way of modeling a function of a time series. And at the time, I started telling you about things like, oh, we want to, do sepsis detection on a time series, or, want to classify handwriting or something like that. But an equally fine thing to try and do is to try and classify real time series versus fake time series generated from an SDE. And this is exactly what I'm doing here. So I've written it down in a slightly different form. I'm adopting a kind of stochastic notation convention instead, but that's not really important. And you can see what I've done is I've just written down an SDE exactly like you already saw, and it's some state that is a function of where we started, and then it's this controlled differential equation, basically exactly like you saw before. And then once again, I need to define some output. And once again, that output is going to be a function of my hidden state. My hidden state evolves in the latent space. And in this case, the function I happen to have written down here, I could have done other things. In this case, it just happens to be just a dot product between some learned vector and some h of t. If I wanted to, I could have made this a neural network or a feed-forward network or whatever, right? And so overall, what I'm saying here is I'm saying that this learned function of my output, of my data, of my model output or of my data, is going to be defined via the evolution of a controlled differential equation and then a function off the end of that. And okay, I've told you a lot of equations now. Maybe this is starting to feel like quite a lot to fit in your head. So this is the summary. And if that looks like a lot, this is everything I've already told you. There's nothing new here. These are just the equations I've already written out, and I've just put them in one spot. And as I work from top to bottom, it follows the formulation of a Gan. Noise goes into a generator. Output of a generator goes into a discriminator. That's a Gan. As I work from left to right, it follows a differential equation. I have some initial condition. I evolve that according to my differential equation, and then I get an output. So the summary here, as I say, is just everything you've already seen before. And hopefully, I mean, this slide will be up for a short while, and hopefully you can stare at that for a little bit and convince yourself that this is the way everything has been built up. So the summary is a neural SDE, as I've introduced them, and a neural CDE, as I told you about them much earlier, collectively form this generator-discriminator pair. And so arbitrary drifts and diffusions are admissible, by which I mean, look at this middle box here. This is the SDE. And I told you, quote unquote, any SDE can now be modeled. This is what I'm saying. Quote unquote, any SDE can be learned. So this is a very, very flexible way of modeling time series. And the thing I really like about this is that I haven't really used anything beyond what people have been using for decades. I've taken the standard off-the-shelf SDEs that people have been using for decades. And all I've really done is I've said, okay, I'm going to make my vector fields be neural networks. I'm not going to derive them theoretically. I'm going to make them neural networks. And I'm not going to use these fixed statistics, these fixed f. I'm going to learn my f. It's called a discriminator. It's called a Gan. But basically, nothing has really changed. And so it's really these same fundamental techniques that we've had all along. Okay, now let's move on to the pictures. Let's look at some examples of doing this in practice. So here's the first example of how we might use this. So this is just Brownian motion. This is a nice and simple example. I've looked at my computer. I've had it simulate Brownian motion for me. That's the blue, and then I have, hopefully to no surprise, been able to fit an SDE to Brownian motion. And maybe this feels like a sort of like slightly trivial example. And the reason I use this is to really justify that SDEs are a thing worth considering beyond merely like a random ODE, or if you know what I mean when I say like a latent ODE model. This is an example of something that you couldn't really model with an ODE. And you really need this randomness coming in at every time. And that's no surprise, right? People invented SDEs decades ago because they wanted to be able to model things that they couldn't model with ODEs. Okay, let's do something slightly more complicated. Here you can see we've got this positive drift, we've got some diffusion, we've got some mean reversion, and once again this is an SDE, and once again we can model this with a neural SDE. Okay, let's make it slightly more complicated. We can do things like time-dependent diffusions. Nothing's very complicated. Nothing really changes here. This is the same code, by the way, for all three. It's just a different data set. And then also, once again, we don't have to stick to univariate things. We can do multivariate things. This is a stochastic Rnns attractor, a chaotic system. And yes, once again, we can fit an SDE to this data set. Okay, so I've been telling you that we can fit neural SDEs to SDE data sets. Maybe that's not surprising. The real test is, of course, does this work on real things? And yes, the short version is that it does, at least to the level of academic rigor. So this first one is one I quite like. It's a financial example. I think these are the evolution of the midpoint and spread over a couple of minutes of a data set of a couple of years, and then having taken all those little slices, and then we try to model this evolution of the market over these couple of minute time intervals. And then we've got another example here. So actually, this is one I really want to focus on. I think is this Beijing air quality one. This is an example of I think it's 6-dimensional and indicates how different markers of air quality, things like what's in the air, how much particulate matter there is, how does that evolve over the course of a day? So I look at Beijing, all right, and I get some time series that says this is how it evolves over the course of a day, and then I do it again the next day, and I do it again the next day, and I get some data set of time series. And now I try to model that using a stochastic differential equation in exactly the way I've been describing. And once again, the short version is that this works. You can do this. And the reason I like this as an example is because this is something for which I have no theory. I have absolutely no theory telling me how air quality evolves and how particulate matter changes over the course of a day. That's unlike finance, right? People have spent a lot of time figuring out theories for finance, but I don't have that for air quality. But that doesn't stop me, right? I can substitute theory for data, and now I can fit my model to that data. And this is an example of something which is, I think, normal in deep learning, but I think relatively new in differential equations.
Oh, one thing I think you can say that is strong is that there's a sense in which neural SDEs generalize latent ODEs. So you sort of can't not win, right? You just have a stronger model class. So.
Yeah, that's totally fair. Yeah, I agree. Okay, now there's lots of things I haven't told you about. I've been trying to keep the complexity down, keep this understandable over the course of this talk. So things I haven't told you about. I've not told you about how you parameterize these vector fields. I've just been sort of waving my hands and saying feed forward neural network. I've not told you about the details of this training that classically appears in GAN training, things like choice of optimizer, things like tricks like stochastic weight averaging, ... There's a whole literature of GAN training tricks. All of which, by the way, is just inherited directly from the GAN literature. There's things like, once again, how do you impose Lipschitz regularization of the discriminator? Again, something coming out of the GAN literature. How do we do this? There's a couple of different choices here. What is your choice of SDE solver? I've been telling you there is an SDE solver. I use an SDE solver, but which one? What are the choices? What are the trade-offs? In particular, there's a lot of our recent work has looked at reversible SDE solvers. This is something which turns out to be very helpful, and I'm not getting into that now. How do you simulate the Brownian motion? What other training strategies are there? I've been telling you about GANs. These are sort of the ones that I think are the highlight for me, but you can look at other things as well. And then applications. Unsurprisingly, finance folks are interested in this. And then finally, there's also connections to lots and lots of other things. Anyone who's been looking at score-based diffusion models, these are recent class of models based off of SDEs. So unsurprisingly, it looks like there's probably something there. So we have a couple of papers doing this. So as I say, lots of things I haven't told you about, but basically everything on this slide is either standard in either the differential equation literature or in the deep learning literature. And if you're really curious, as I say, we have a couple of papers on this. Okay. Now, if as I said, if you're not that familiar with SDEs, don't worry. We've gotten through this because now I'm going to start telling you about software instead. So we're going to chop and change, and we're going to move on from one topic to the next. So we're now on to the final bullet point from that program I had on my very first slide. I'm going to tell you about software. Modern frameworks, these are really amazing things. The big three, I think, are undeniably PyTorch, JAX, and Julia. So why are these so great? Well, I mean, probably I'm preaching to the choir here. You can now run your scientific models on the GPU. You can now backpropagate through them without writing derivatives and things by hand. So this is great. These are tools that we should really be using and making the most of. What is the backbone of huge amounts of scientific computing? Differential equation solvers. And so it is in reflection of that I'm very happy to introduce Diffrax. These are differential equation solvers written in JAX. So I'm going to really start getting into the meat of what's new here. What can you do with these that maybe you couldn't do with other frameworks before? But first of all, let me just justify to you that it has all the things that everyone else already has. So Diffrax has lots of things. It has things like ODE solvers, SDE solvers, and CDE solvers. That last one is new. Most people don't have that. It has high order solvers, implicit solvers, symplectic solvers. You can get dense solutions, that is to say, not just an output at individual times, but you can get a continuous time path as an output by sort of joining up the dots in a smart way. You can backpropagate in different ways. Probably most of you have heard of the adjoint method. There's actually a lot of the adjoint methods out there. There's lots of ways to backpropagate to a differential equation. Diffrax implements these. I say support for neural differential equations. This is more of a motivator, but this is what I have in mind when Diffrax was written. Advanced step size controllers. So there's multiple ways of doing step size control, adaptive step size control. Once again, this is available. One of the things we inherit from using JAX, I don't know, I'm guessing people have used different frameworks before, but those of you who have used JAX know what I mean when I say VMAP, which basically means parallelization. And we can parallelize over anything. The one that you see in most libraries is that you can parallelize over the initial condition. You can solve the same differential equation from lots of initial conditions. But because we're using JAX, then other things we can parallelize over completely for free, no real change needed. You can parallelize over the region of integration, for example. You can solve the same differential equation over different regions of integration. this ends up being useful for lots of the CD and SDE time series stuff I was telling you about earlier on. You could, for example, parallelize over solver tolerances. So when you solve a differential equation, you might say the relative tolerance is this, the absolute tolerance is this. Can I now solve my differential equation over multiple different tolerances, get like a work precision result or something like that? Yes, you can parallelize over that too, etc. Anything that goes in, you can parallelize over it. Those of you who have used JAX know what I mean when I say a pi tree. You can use arbitrary pi trees as state. Those of you who haven't used JAX, don't worry about it. And then you can also do things like handle discontinuities in the vector field, which is one of those things that's kind of like fiddly to handle if you don't have built-in support. So there's lots of things in there. This is just a few of them. And so now I'm going to slightly ambitiously, this is the thing that always goes wrong in a presentation, try a live coding demo. So this is mostly just going to be to demonstrate the API because I'm aware that time is getting on, so I won't try and do anything too much here. So let's start by importing a bunch of stuff. Okay, so let's just do something very simple, and I'm going to do exponential decay. dy dt equals minus y. That's my exponential decay.
Oh, sorry, Patrick, I think your text is too small. Can you, someone's asking to zoom in, and yes, thank you.
Let me know if that's not enough. So now I'm going to wrap this up and say this is for solving an ODE. And what this is formally what I'm saying here is that this is that dt. If I think of this as an SDE, just forget the Brownian term for a second. But if you think about writing this down as an SDE, right, you write down dy equals f dt. So I've written down my f, and now I'm telling it that there's a dt that pairs with it. And then actually, let's do the solver next. So let's do. So Diffrax is one many of you may have heard of, Dorman Prince 5.4, standard ODE solver. And then specify our region of integration and where we want to start from. And then I just, actually, sorry, also I need to tell you the, let's pick the initial step size automatically. That's what dt naught equals none does. My solution. Now this will take a short while. Oh gosh, that's not good, is it? Oh, sorry, I've used a constant step size. Let's not do that. So I'm gonna recant on my initial step size selection. I'm gonna set it manually like that. Okay. So let's do.
I think the text is a little small again.
Yeah, don't worry, I'm going back to it. Okay, there we go. So now I get a solution. Sorry, ignore the previous error. That was on me. Okay, so we get a solution to our differential equation. Now, you probably didn't notice because I was busy talking, but this actually took a short amount of time for that to happen. But if I should do it again, it'll happen instantly. And the reason for that is because under the hood, it's all being compiled. And so that first time, we hit the JIT compiler, and it went ahead and produced some optimized code. And then the second time around, we just hit the same JIT compiled thing. And that happens very, very quickly, almost instantly. And I can inspect the solution, and I can tell you that, well, it started from T0, it goes to T1. The outputs, by default, we save it at just the end. And at the end, we got this value here. Okay, so I can solve exponential decay. That's nice and simple. Let's do something slightly more complicated. This is where I'm going to start to show off some of the new things that happen in Diffrax. Because what I'm going to do is I'm going to solve an SDE, and we'll do it with say with dense output. So in this case, let's start off. So this is the same exponential decay for the drift of an SDE, and then for the diffusion, let's just have a small amount of noise. So, okay, and now this term thing, previously I had ODE term. What am I going to do now? I'm going to do something that looks a little bit like Lego and just sort of put things together. And actually, so first of all, I also need to define a Brownian motion. Let me do that. So T0 equals T1, T1 equals that. And I need to import something, my bad. Okay, so those of you who are familiar with JAX know that you need to explicitly work with some randomness. So let's do that now. Okay, so I've got a Brownian motion. So we need some kind of input, some sort of random input into a differential equation, into our SDE. And so this is our Brownian motion. This is how we're going to do it. And then we do the Lego. What does this say? This says, well, I have a drift term, and that is drift dt. And it says I have some sort of diffusion, dw, d Brownian motion, and my diffusion is diagonal. And so that specifies the interaction between my diffusion matrix and my Brownian motion. And now maybe let's use, say, the Euler solver. And now let's specify that we want to get dense output. I told you that we could do that earlier, so we can do that. Okay, and now, again, we can do our differential equation solver, term solver T0, T1, dt0, y0. And then I need to specify that new save at thing that we do that. So once again, it takes a moment. So it takes a moment to compile. And then now we have our solution. And if I do that again, you'll see we get the answer instantly. And now, because I got this dense solution, then I actually save the output nowhere at all by default, but instead I can now evaluate this at, say, 1.1. So I've scrolled accidentally. Okay, I can value it at 0.2, 0.3. Sorry, I'm still there. There we go. And so you can see we're now getting this output at arbitrary times. And that's what I mean when I say a dense solution. So as I said, I'm not going to spend too long on this. This is just sort of a quick API demo to sort of give you some flavor of how Diffrax is like to work with. And as I say, it's kind of like a little bit like Lego. We're sort of building up these different objects here. Okay, so I'm now going to alt tab back to the presentation because there's a lot of cool stuff going on here under the hood that is new to Diffrax relative to other libraries. So the internal structure is pretty cool. And what is it? And I told you at the start, controlled differential equations are going to keep coming up, and this is part of why. ODEs and SDEs, these are both reduced to CDEs and solved in a unified way. If you think about an ODE, you can see I've written it down like this. And if you think about an SDE, once again, standard looking SDE, nothing special there. And if you think about both of these are both special cases of that CDE I wrote down earlier. Those of you who are familiar with the mathematics of SDEs maybe have a few, hang on a second, concerns at this point. You can justify this. I'm not going to get into that. But you can see I've written down a controlled differential equation. And you can see that, like, if you think about taking this controlled differential equation and just setting x of t equals t, that's my input path, x of t equals t, then that's the same as an ODE. If you write down x of t is t comma w of t, so if my input path is just time and Brownian motion, then I recover an SDE. So you can see that there's this abstract notion of a controlled differential equation that is more general than that of an ODE or an SDE. And because we're working with this as the framework, then we can simplify the internals of the library a lot. So as a really nice example of this is think about writing down Euler's method. Probably most of you have seen Euler's method for ODEs. It looks like this. It's just standard, simplest possible off-the-shelf solver. And if we write it down for SDEs, we can see that it's basically exactly the same thing. You can see I've written down the same thing, and then I've just written down the same thing again, but with the stochastic term. And kind of nothing has changed. And so overall, what you can see is that if the right-hand side of a differential equation solver, pretty much ubiquitously, what you always see is a vector field, a difference in this control, and then some bilinear operation, multiplication, for example, combining the two together. And I see we have a chat question. Could you okay, that's fine. Okay, and so basically by using this as the starting point, we can then write down the same Euler method for both ODEs and SDEs. And moreover, we can do that for lots and lots of other things too. So these are the implications. The code complexity, the internals of the library is really, really simple. Or is dramatically reduced, that is to say. So we can write down the same solver that works for all kinds of different things. If you want to think about more advanced things like different ways of backpropagating, then you might have heard things like the adjoint method, optimize and discretize, blah, blah, blah. There's lots of different ways of differentiating through a differential equation. This is kind of complicated, but the good news is I only have to write it down once. That's in my thesis, actually, if you're curious about more details there. The same set of abstractions can handle lots and lots of different kinds of solvers. So if you think about, say, like just a standard Runge-Kutta method, like an Euler method, then you have Y, and you just have this single evolving state. There's kind of no complexity there. But if you look at, say, a symplectic method, then typically you partition your state into two parts and they interact in a particular way. And actually, once again, it turns out the same abstractions can handle these other kinds of things as well. et cetera, et cetera, et cetera. The basic idea is that ODEs and SDEs can be handled with the same code. It handles advanced use cases really, really well. So for example, maybe I want to solve an ODE and an SDE at the same time. Maybe one is an input into the other. Maybe there's something going on there. I can do that because I'm using the same abstractions for both. If you look at, for example, here a controlled SDE, and this is the kind of thing, once again, you start trying to do complicated stuff and these sorts of things kind of start appearing. You can see I've got multiple drivers here. I've got a DW, that's the Brownian motion. I've got a DX, this is some control. How do I do this? This is something which is very easy to do in what I've been laying out, because you saw I had this multi-term ODE for the drift, wiki-diagonal control term for the diffusion. Well, I can just add another control term. I can put multiple terms together to make that happen. When you're working with new solvers, a lot of these have particular requirements. So if you think about, say, an Euler method, then this just treats this FDW as a matrix vector product. It doesn't want to do anything clever. But if you start looking at more advanced solvers, something like, say, Neural Vectoire, and I realize probably none of you have even heard of this, but there are much more complicated differential equation solvers out there. And in this particular case, this actually wants to decompose that matrix vector product into individual terms and treat each piece separately. And so what we're seeing here is something which these are abstractions that from you as an end user, you don't have to worry about them. You're still just saying, please solve an ODE. But for those of us who are developing differential equation libraries and those of us who sort of care about this kind of thing, then I think this makes several advances here in sort of pinning down the abstractions that really help work with these things. I guess what I'm saying here is that, like, obviously Diffrax is not the final word in differential equation libraries. Obviously, in the next 10 years time, if not before, someone will write some other very, very cool differential equation solving library. Hopefully these abstractions that I've introduced here can be used there too. Okay, what else? Diffrax is fast. It's lots faster than Torch diffeq. The basic point is that Torch diffeq is written in PyTorch, those of you who are familiar with Torch diffeq. But because it's written in PyTorch, there's an overhead of the Python interpreter. We don't really want that. It seems Diffrax seems to be getting similar speed to differential equations.jl over in Julia. I've not done like precise benchmarks on this yet, but just sort of like initial ones seem to suggest that it's very, very similar. Diffrax is highly extensible. Again, this is one of the things I really like about the abstractions we've used here. You can manually step through it yourself. For example, if you're using a differential simulator, you want to handle the stepping yourself and it'll just pass it off to some diffeqs solve function. You can do that. You can write your own solvers. The Diffrax has a lot of abstract-based classes. You can easily add custom operations. There's an example I really like for this, which is sort of taking a step back, 10,000-foot view, getting a bit philosophical for a second. A machine learning model is held to be good if it generalizes, if it keeps working on the things that you didn't explicitly train it for. The same is true of, say, any model in physics, right? We construct models in physics with the idea that we look at the data we have, and then the true test of is this a good model is, can we produce new hypotheses that are true using this model? The same is true in mathematics. An abstraction is something which is, it's useful if you can use what you already know about something and generalize it to tackle a new problem. And now in Diffrax, it turns out that everything I've been presenting to you was based on the idea of, can we solve ODEs and SDEs in a unified way? But it turns out that it generalizes. And so recently I've been discussing with someone, how do we handle semi-explicit differential algebraic equations? And it turns out you can handle these in Diffrax as well. I didn't even design Diffrax to do this, right? But the abstractions are such that this is still possible. And so I sort of make the weak claim that this is because Diffrax has set up the correct abstractions for differential equation solving in some sort of generalized high-level way. And this means that even like as an end user of the library, even though I haven't built in pre-built support for this, you can still just write your own differential algebraic equation solvers and it will just work. And I see we have a few Q&As that have popped up. So let me go through. Okay, so Chris, while ODEs and SDEs can be written in the form of a CDE, higher order SDE solvers do need to do some very different operations. Yes. So for example, does Diffrax support higher order SDE solvers and approximate non-commutative iterated integrals? What about higher order, strong order methods? From the docs, it seems like this is something that's not quite supported. Right, so the short version is that this isn't in Diffrax at the moment, but it is possible with the abstractions that have been laid out. So Diffrax supports higher order solvers in the sense of things like Milstein's method for particular noise types. And then if you want to handle things like Levy area estimation, then you can do that too. I just haven't written that down yet. Similar speed. Do you have code for benchmarking the Brusselator? Seems to be about 500 times slower on this standard benchmark, but I could not find the documentation how to do things like KLU solving sparse arrays. I haven't tried Brusselator in particular. I've been trying other things instead. I would be skeptical about claims of running 500 times slower. It may be that you're timing things like JIT compilation or something, or possibly any number of other things. If you're curious about that, Chris, feel free to reach out to me, because I do want to ensure Diffrax is really as fast as it could be. Any hope on cross compatibility with PyTorch? Realistically, unlikely, I think. Diffrax is very much built on top of the JAX framework. So I think with PyTorch, you're probably stuck with Torch diffeq. For semi-explicit DAEs, how are you handling the initializations? There's a lot of classical literature that says ODEs are not DAEs due to the initialization. Short version, I'm not looking at the complicated aspects of that yet. If you're curious about this, go and look at, it's one of the issues on the Diffrax GitHub that specifically says, can we handle DAEs? And the focus there is on how do you write down the solver. So I'm kind of giving you a non-answer there, but that's where we're at. Okay, so yes, Diffrax, it exists on GitHub. Do go and check it out. And I'll put this link up again in a second, because I am now at the end of my talk. So these are the references I've been working through. And the summary, this is the final slide, is that way back now, over an hour ago, this exists, thesis/textbook. Do go check that out for an overview of neural differential equations in general. The SDE work I've been telling you about. So these are a couple papers on this. The first one is really sort of laying out this, as the title suggests, neural SDEs as GANs. And then the second one is starting to delve into the details of this and how do you actually handle some of the complexities of making this work efficiently. And then finally, Diffrax is available on GitHub. So feel free to message me if you have any questions. And all that remains to say is thank you very much for your attention, everyone. You've been a great audience. And do we have any more questions now?